The first problem says that to anticipate the dip and hump in a road, the driver of a car applies her brakes to produce uniform deceleration. Her speed is 100 km per hour at the bottom A of the dip. So A point is the bottom of the dip and the speed at that point is 100 km per hour. But she applied the brakes at this point and then the car had negative acceleration, and at point C the speed actually was 50, like half of the initial value. So here the speed was 50 km per hour, right, at the top of that point C, right, and the distance from A to C is 120 meters, right. If the passenger experience a total acceleration of 3 meter per second square, so the total acceleration at A is 3 meter per second square, right. It is not the component of acceleration but the total resultant acceleration, right. And if the radius of curvature of the hump is 150 meters, right, calculate for example the radius of curvature rho at A, right. So at this point C we have given another information, and that is rho is equal to 150 meters, right. The distance from A to C is obvious, it is from A to B 60 and B to C 60, so total is 120 meters. First thing to determine is the rho value at A, right. So this depression is a curved path, and what is the corresponding radius of curvature for that? The radius of curvature for this concave down curve at point C is already given, 150 meters, right. Second thing to determine is the acceleration at the inflection point B. So acceleration at point B need to be determined. We can readily say that it will only have the t component of acceleration, no n component at point B, but at point A and C it will have both components, a sub t and a sub n. The information about radius of curvature should tell you that you should resolve the acceleration into n-t coordinates, or in other words this is a problem related to n-t coordinate system for describing the curvilinear motion, right. So the acceleration at the inflection point, and third thing to be determined is the total acceleration at point C. So at point C acceleration will have both components, a sub n, a sub t, and we need to determine this total acceleration, which will be a sub n square plus a sub t square root, right. So now let's clearly write what is given to us. One thing obviously that we will assume that the cars and passengers, they both can be assumed to be a particle for the sake of this problem, right, because the actual dimensions of car doesn't play a role in our calculations, right. Similarly, the actual weight of the car and other properties of the cars and passenger are not relevant to our problem. So given information is that there is a constant deceleration from A to C. Second thing is that distance A to C is given 120 meters, the whole distance. At point A we have two information, total acceleration, like the magnitude of the total acceleration vector is given 3 meter per second square, and velocity is given 100 kilometer per hour. At point C again two information is given. We are given with the rho value and velocity value, which is reduced to 1/2 of the value at point A, and another information is given is that the B is the point of inflection, which means rho will be infinity at that point, right. We need to determine three things: rho at point A, total acceleration at point B, which is the point of inflection, and total acceleration at point C, which is the concave downward curve, peak of the concave downward curve, right. Now since we need to determine rho, and we know that the acceleration's n component is v square over rho when described in n-t coordinates, so the first thing you should come in your mind is that a sub n is equal to v square over rho. At point A, if we apply this expression, v is given but rho is not given, right. Instead the total acceleration is given at point A, right. So if we, for example, write the total acceleration, which is 3 meter per second square, which is given, and A sub n contains rho quantity which needs to be determined, V is given, it means the first thing we should determine is this A sub t, right? Because if A sub t is known, we can have already A which is given, and A sub n is V square over rho where V is also given, right? So then we can put it in this expression to calculate for rho back, right? So therefore the first thing to determine actually for part A is to calculate what is A sub t, so that we can put it in this expression, and this A is given, so we can determine A sub n, and then we can put A sub n here to calculate rho, right? So the first step should be to determine A sub t, acceleration's t component, right? So for that, again if I go back and look at the situation which is given, we have 2 points A and C, and the velocity at both of these points are given, right? And the tangential component from A to C need to be determined, right? So the first thing which should come in your mind is that the initial and final velocities are given, right, between 2 points. So the expression which should be readily applicable should be that equation 3, if you remember, right? Because it says that the acceleration remain constant, it is a constant deceleration case. At point A, the brakes were applied, and then at C, the velocity reduced to half, right? And there is a constant deceleration, uniform deceleration between these 2 points, right? So in the constant acceleration case, think of a expression in which the initial and final velocities are given, and you need to determine acceleration in between, right? And that is actually the equation 3, which is V square is equal to V naught square plus 2A S minus S naught, right? It is an equation which is relating the velocity at a particular instant if the velocity at some previous instant was given, and you need to determine acceleration, or for example you need to determine final velocity if the acceleration, constant acceleration in between is given, right? So that equation we should apply now with S equal to 120 meters, V sub c final velocity or the last velocity 50 kilometer per hour, and the initial velocity or the starting velocity is 100 kilometer, which is V sub a, right? And the acceleration will actually become the A sub t, or the tangent component of acceleration, and it should be deceleration. Actually later on when we actually determined, it came out to be negative, confirming that there is an actual negative acceleration between A and C. So I applied this formula in the t direction or t component, right? But one thing you need to please remember that there is no constant t direction between A and C. T direction is varying all along from A to C, right? So I cannot simply draw that this is the t axis, this is the t axis only at point A. At the next instant t will change, next instant t will change, right? But the magnitude of the t component will remain constant deceleration, which we will determine using this expression now. So I have rearranged that equation, right? And I can put simply S as 120 meters. Vc and Va need to be converted to meter per second. So this 1000 is actually conversion from kilometer to meter, and this 60 by 60 at the bottom is to converting from hour to seconds, right? When I determined A, it turned out to be negative 2.41 meter per second square, right? So now I already have A sub t. I can simply put this in this expression. The total acceleration's magnitude was given to us in problem, 3 meter per second square. T component we have already determined, it is minus 2.41. I can calculate the n component, and that will be 1.785 meter per second square. It is in positive units, so which means the direction of this A sub n should be towards the center of curvature. So at this point if I go back, the direction of this A sub n should be like upward because it is an concave upward curve, right? And that came out to be, the magnitude came out to be 1.785. Now I already know that this an is equal to v square over rho. V is given at point A, 100 kilometer per hour, right? Again converting to meter per second. And A is also determined already, so 1.785 meter per second square. Rho will come out to be 432 and it will be in meters because it is a radius of curvature, a length quantity, right? So first part is done. The second part was to determine total acceleration at B, and we know that total acceleration at B will be simply the t component of acceleration. An will be 0 because B is the point of inflection, and we have already determined the A sub t, and that will be a constant value which is equal to minus 2.41, right? So it means that at point B acceleration will simply be equal to minus 2.41 meter per second square. So A sub n will be 0. So the total acceleration at B simply will be minus 2.41. But again I would say that at point B this minus 2.41 do not have the same direction as this minus 2.41 at point A, right? So both are the magnitudes of the t components at two time instants, right? But their directions are different. So currently we are talking in terms of magnitudes or scalar quantities. So for example, I can write it here that it is minus 2.41. So it may have some direction at point A which will be like this. In minus t direction, we will see towards the end what will be the direction of minus t. So this 2.41 will have a different direction at point A, meter per second square. But at point B, it will have a different t axis, right? So this minus 2.41 at point B will have a different direction. So it is again minus 2.41 meter per second square. So its negative t axis will be different than the negative t axis at point A. Similarly, at point C also the negative t axis will have a different direction than from A or B, right? So magnitude of t component is constant deceleration between A and C, but their directions are changing. And actually the change in direction of acceleration is taken care by the second component A sub n. So the third case was to calculate total acceleration at point C, and we know that at point C it should have both components now. So I can apply the total acceleration equation, the sum of n component and t component. N component is simply v c square over rho. V c square was given, rho was given, so it's a direct determination, but you need to convert velocity into meter per second from kilometer per hour. You will determine A sub n. A sub t will remain same because it's a constant deceleration between A and C. So the t component at C will be same as the t component at A. The magnitude of t component will be same. So therefore we can write the total acceleration vector as the n component which we have just determined, 1.286 times E sub n, the unit vector in n direction, plus minus 2.41 times unit vector in t direction, right? So this will be the total acceleration vector, but the thing which we need to determine is the resultant acceleration. That will simply become A sub n square plus A sub t square root, and that will come out to be 2.73, right? So total acceleration at point C or top of the hump will be 2.73 meter per second square, right? Graphically, let's write both the n and t components at all 3 points. So at point A, if you remember, the curve was like this. It was concave upward. A point was the deepest point of that curve, right? So at point A, I can draw the positive t and positive n axis. Positive t axis will be towards my right, positive n axis will be towards center of curvature, which will be somewhere here, for example, right? So I can write the acceleration vector, both components, in using these two axes now. A sub n was positive, so it should be upward towards center of curvature, and its value was 1.785. We calculated that. A sub t was negative, and it was having a magnitude of 2.41. So I draw it towards negative t direction, and the magnitude is 2.41, which should give me the direction of resultant somewhere diagonal direction between both components, and the magnitude of that diagonal or total acceleration was also given in the problem, that was 3 meter per second square. At point B, it was the point of inflection, so it has only t component, but the value which we determined was minus 2.41, which means it should be negative t direction. So I draw it in the negative t direction with a value equal to 2.41 meter per second square, right? No n component, right? So this is the n direction, so no n component in that direction. The point C was the peak of the hump, so it is a concave downward curve. So center of curvature will be somewhere, for example, here, right? And at point C we determined the normal component to be 1.286. It is a positive quantity, which means it should be towards center of curvature or plus n direction, and the A sub t is a negative quantity, so it should be towards the minus t axis and with a value of 2.41. So see, A sub t a different direction with A sub t here, right? Again, this A sub t is a different direction than A sub t on point C. These two an and at components give us the direction sense of the total acceleration vector, which should be somewhere diagonal downwards, and its magnitude we determined as 2.73 meter per second square, right? And we can also see that this radius of curvature was given also as 150 meters. We determined that radius of curvature, actually that whole distance, to be a very large number. It was in point A, and that was 432 meters, right? It is measuring from a center of curvature which will be located somewhere above the curve, having a distance from that center to exactly point A is 432 meters, right? So that should be radius of curvature. This distance from C to this center of curvature is given to us as 150 meters, right? So it means that at A point, the curve is part of a big circle having a radius equal to 432 meters, and at point C, the curve is part of a big circle which is having a radius equal to 150 meters, right?